When it comes to dimensions, most of us intuitively understand the notion that space possesses those properties. You can move forwards or backwards by any amount you desire in any of the three dimensions, up, down, left, right, or forwards, backward, in which motion is possible. It's why if you ask yourself to draw a path that describes the shortest distance between any 2 points, most of us will give the same answer that Archimedes gave more than 2,000 years ago, a straight line. This intuitive answer correctly describes how the three dimensions of space work in our universe. In flat space, the shortest distance between any 2 points is a straight line. This is true regardless of how you rotate, orient, or otherwise position those 2 points. However, our universe doesn't simply possess the three familiar dimensions of space, but rather 4 space-time dimensions. Oh well, 3 of them are space, and 1 of them is time, and that's where we get space-time. And that's true, but not the full story. After all, the shortest distance between 2 space-time events isn't a straight line at all, and moreover, time is a fundamentally different type of dimension than space. Here's how it actually works. When did you first realize that the shortest distance connecting any 2 points in space is going to be a straight line? In fact, that realization, as far as human knowledge is concerned, comes from a place we might not realize: the Pythagorean theorem. You might remember the Pythagorean theorem as a rule about right triangles, as it notes that if you square each of the short sides of a right triangle, A and B, and add them together, that equals the square of the long side. Mathematically, if we call the short sides A and B and we call the long side C, then the equation relating them is a square plus B square equals C square. Think about what this means, however. Not from the perspective of pure mathematics alone, but in terms of distances. It means that if you move through one of your spatial dimensions by a certain amount, A, for example, and then move through a different perpendicular dimension by another amount, B, for instance, then the distance between where you began and where you wound up is equal to C, as defined by the Pythagorean theorem, where everyone at all locations, at all times, and irrespective of motion, all agrees on the same coordinate system. In our universe, of course, many of these things aren't universally true. For example, we're not restricted to living in flat space, such as a flat sheet of paper. We live on a spheroidal Earth, for instance. We have not just length and width dimensions to our universe, but depth as well. How would we then figure out what the distance is between any 2 points in space? Perhaps surprisingly, we'd use the exact same method as we used in 2 dimensions, except with 1 extra dimension thrown in. If you can measure or know the amount your 2 points are separated by in those 3 independent, mutually perpendicular dimensions, the x direction, the y direction, and the z direction, you can figure out the total distance between them by using the same method as earlier. The only difference is, because of the extra dimension, the distance between them, let's call it d, is going to be given by d equals under root x square plus y square plus z square. This might look like a scary equation, but it just says that the distance between any 2 points is defined by the straight line connecting them, the line that accounts for the separation between your 2 points in all 3 dimensions, the x direction, the y direction, and the z direction combined. Thinking about distances like we just did provided a great description of what we'll wind up with if we consider flat, uncurved space on its own. You might think, well, if time is just a dimension too, then the distance between any 2 points in space-time will work the same way. For example, if we represent the time dimension as t, you might think the distance between any 2 points would be the straight line connecting them in the exact same way. In mathematical terms, you might think that the equation for the separation between any 2 points would look something like d equals under root x square plus y square plus z square plus t square. After all, this is pretty much the same change we made when we went from 2 spatial dimensions to 3 spatial dimensions. It's a reasonable step to attempt and describes exactly what reality would look like if we had 4 dimensions of space rather than 3 of space and 1 of time. But that actually makes for a huge difference. Instead of 4 dimensions of space, the fact that we have 3 dimensions of space and 1 dimension of time requires us to look at the puzzle differently. Despite what your intuition may have told you, time isn't just another dimension, the way spatial dimensions are familiar dimensions. There are 2 fundamental ways that time, as a dimension, is different from your typical spatial dimension. The first way is a small but straightforward difference. You can't put space, which is a measurement of distance with units like feet or meters, and time, which is a measurement of, well, time with units like seconds or years, on the same footing at each other right from the start. You have to have some way to convert one of them onto the same footing as the other. Otherwise, you would be attempting to link together two fundamentally different types of quantity. You would be very upset if you asked me the distance from New York to Los Angeles and I told you it was 13 milliseconds. Fortunately, one of the great revelations of Einstein's theory of relativity was that there is an important fundamental connection between distance and time, the speed of light. Any particle or phenomenon that travels through the universe without a rest mass moves at this speed, including photons, gluons, and gravitational waves. The speed of light in a vacuum, 299,792,458 meters per second, tells us precisely how to relate our motion through space with our motion through time. When we use terms like 1 light year or 1 light second, we're talking about distances in terms of time. The amount of distance that light travels in 1 year or 1 second, for example. 13 milliseconds is the amount of time a photon would take to traverse the New York-Los Angeles distance. If we want to convert time into a distance, the way to accomplish that is to multiply your duration by the speed of light in a vacuum. However, there's also a second way that time is fundamentally different from space as a dimension. And this second difference requires an enormous leap to understand. In fact, it's a difference that eluded many of the greatest minds of the late 19th and early 20th centuries. The key idea is that all observers, objects, quanta, and other entities that populate our universe all actually move through the fabric of the universe, through both space and time, simultaneously. Even if you think of yourself as being at rest, by simply sitting where you are, stationary and not moving through space at all, it turns out that you're still moving through time while you're motionless through space. Moreover, there's a very specific rate for the passage of time that we're all familiar with. Time passes at the rate of 1 second per second. However, and this is the key point, motion through space isn't just possible but occurs all the time. It turns out that the faster and the greater the amount you move through space, the slower and the lesser the amount you move through time. No other dimension has this property. The spatial dimensions are not like this at all. Your motion through the x dimension in space, for example, is completely independent of your motion through the other two, y and z spatial dimensions. However, it's your total cumulative motion through space, as measured relative to any other observer, that determines your motion through time. The more you move through one of them, either space or time, the less you move through the other complementary quantity. This is the underlying reason why, when you move at speeds that approach the speed of light, you start to experience phenomena such as time dilation and length contraction, aspects of reality that are essential to Einstein's relativity. If you only move at very low speeds compared to the speed of light, it's very difficult to notice these effects. Time appears to move at 1 second per second for everyone, and lengths appear to be the same distance for everyone at speeds normally achievable on Earth. But as you approach the speed of light, or rather as you perceive an object where the relative speed between you and it is some significant fraction of the speed of light, you'll observe that the object that you see as in motion relative to you appears to have its length contracted along its direction of relative motion, has time or clocks on board it appear to run at a slower, dilated rate, cc. The reason behind these phenomena, as first realized by Einstein, was straightforward. It's because the speed of light is a truly universally invariant quantity. In other words, the speed of light in a vacuum is identical for all observers. If you imagine that a clock is defined by light bouncing back and forth between two mirrors, then watching someone else's clock as they move close to the speed of light will inevitably result in their clock running slower than your own, even though you both perceive time as running at that 1 second per second rate from your individual frames of reference. In a great twist of fate, the person who first put these puzzle pieces together was Einstein's former teacher, Hermann Minkowski, who noted in 1908 that, henceforth, Space by itself and time by itself are doomed to fade away into mere shadows. With Minkowski's mathematical rigor behind it, the concept of space-time was not only born, but was here to stay. What's remarkable about all of this is that Einstein, despite lacking the mathematical insight to understand exactly how the dimension of time was related to the three conventional dimensions of space, was still able to piece together this key physical insight. Increasing your motion through space decreased your motion through time, and increasing your motion through time decreased your motion through space. All measurements of space and time are only meaningful relative to the observer in question, and depend on the relative motion of the observer to the observed. And yet, through any transformation you can fathom, the space-time interval will still remain an invariant quantity. No matter who is doing the observing or how quickly they're moving, the combined motion of any object through space-time is something all observers can agree on. In some ways, the success of relativity was made all the more impressive in light of Minkowski's harsh assessment of Einstein from his recollection of Einstein as a student. Speaking to his even later student, Max Born, Minkowski had the following to say: "For me, relativity came as a tremendous surprise, for in his student days, Einstein had been a real lazybones. He never bothered about mathematics at all." Regardless of mathematical ability, the physical insights that, and the only truly invariant quantity is neither distance nor duration, but the space-time interval, were the profound foundation that not only led to Einstein's special and general theories of relativity, and led to our modern understanding of time not only as a dimension, but as a unique type of dimension in our modern four-dimensional conception of space-time. Thank you so much for joining us today. See you soon again in the next video. Until then, good night and stay curious.